Good day, I'm Norman Wahlberger. In today's talk, we're going to be looking at basic measurements in space, with a view to eventually going on to higher dimensions. So going beyond the familiar one-dimensional, two-dimensional, and three-dimensional situations to higher dimensions. And we'd like to know what are the right ways of thinking about measuring in higher dimensional spaces. Okay, so there's a very common assumption that's almost universal these days when we think about Euclidean three-dimensional space. And that is that the basic measurements in our mathematical three-dimensional space are length, area, and volume. So for example, here's our three-dimensional space. If we have a pair of points forming a segment, the natural question is usually, well, what is the length of that segment? If we have a little triangle, CDE, the natural question is, what is the area of that triangle? And if we have a tetrahedron, we generally ask, what is the volume of that tetrahedron? So these are mathematical analogs of physical measurements that we make in our physical space, which are in everyday practice very useful. So there's this automatic assumption, well, that what works in the physical space is naturally going to be working best in the mathematical space as well. That's a big assumption, actually, which turns out to not be correct. Okay, so a very fundamental reorientation is required here as to what exactly the roles of these three things are and what are the right ways of thinking about measurements. So it turns out that signed lengths, areas, and volumes do play a role, okay? But it is much more limited than what is usually imagined. Instead, the quadratic notions of quadrance, quadrea, and quadrume, a new term which we'll introduce, they are more fundamental and general. So up to a constant, quadrance is just the square of the usual length, quadrea is just the square of the usual area, and quadrume is just the square of the usual volume. And there are some constants there that are chosen to make things a little bit pleasant mathematically. But essentially, these quadratic quantities have a big advantage to the more familiar ones. Namely, that they work algebraically much better, and that they don't rely on infinite processes to actually evaluate mathematically. So I've been arguing very strongly in the last few dozen videos that our current theory of real numbers doesn't work really as well as people imagine that it does. But today I want to look at things from a slightly different point of view. So although that's certainly my orientation, it's not necessary to agree with me to understand what I'm going to be doing here. So let's have a slightly different orientation today and ask the following question. How far can we go if we restrict to rational numbers in geometry? The reason we might want to do this is because if we make things work for rational numbers, then we can extend our understanding more easily to other fields, in particular to finite fields. All right, so this is the orientation we're going to have. We're going to just work over the rational numbers and sort of ask, well, how far can we go? What can we do in the way of measuring in three-dimensional rational space? And the context that we're going to be working with are these affine spaces, which are very simply described. So our one-dimensional affine space consisted of affine one points, which were just numbers, rational numbers, enclosed in square brackets, and visualize as usual as a point on the line. So there's the point 3/4. It's an affine 1 point. And then our two-dimensional affine space consisted of affine 2 points, which were pairs of rational numbers enclosed in square brackets, visualized as usual as a point in the usual xy plane. And then we can go to three-dimensional affine space, which consists of triples A, B, C of numbers enclosed in square brackets, and we can visualize that in also a familiar way in terms of axes x, y, and z, say, and there would be the point A equals 1, 2, 3. 1 this way, 2 this way, and 3 that way. So once we adopt this point of view that points are just strings of natural numbers separated by commas and enclosed in square brackets, then it's not hard for us to see how to go to higher dimensions. So we can introduce higher dimensional or n-dimensional space just by considering an affine endpoint to be a list of n numbers enclosed in square brackets. Alright, so it's an attractive kind of framework that allows us to think of space as not just being in one dimension, but there's actually this hierarchy of bigger and bigger spaces, and there's a natural relation between the spaces in the sense that we could identify the one-dimensional space as sitting inside the two-dimensional space, and we could identify the two-dimensional space as sitting inside the three-dimensional space, if we wanted to, and then so on. But there's actually quite a lot of ways of doing that. For example, the one-dimensional space could be thought of as being this line in two-dimensional space, or maybe this line, or in fact maybe some other line as well. And that's going to be an interesting issue that raises up later in this lecture. Alright, so that's our basic orientation to what actually the spaces are that we're considering. Alright, so now when it comes to actually measuring in our various spaces, there were different options that we looked at when we first started talking about that. So in the one-dimensional situation, we talked about the options of considering lengths, or displacements, or quadrances. Let's have a look at what we call displacement, which we might also call signed length. So if we have a directed segment, so a line segment OA, but with a direction, so that there's a first one and there's a second one. And let's say, for simplicity, that the first point is the origin O, and that the second point is the point A with a coordinate x. Then we can define the signed length of this oriented segment to be the length of OA, which is just x. More generally, it would be the difference between the x-coordinate here and the x-coordinate here. So this notion is purely algebraic. It could be positive or negative or zero, depending on the position of A with respect to O. And it is quite a legitimate use of the term length in geometry. So it's certainly not my position that length has no role. In the one-dimensional situation, this notion of signed length is both natural and very reasonable and important. So now let's look at the two-dimensional situation. So we'll consider the analog of a segment, which is a triangle. And for convenience, we'll translate the triangle so that one of its vertices is at the origin O. So here is the triangle O, A1, A2. And we'll suppose that A1 is the point x1, y1, and A2 is the point x2, y2. And we'll think about this triangle as being an oriented triangle, as represented by this little arrow above it. So it means we're thinking about the three vertices as having an orientation. That we go from this one, to this one, to this one, and if necessary, back around. Alright, so that oriented triangle has a signed area. We can associate to it a number, which is the number x1, y2 minus x2, y1 over 2. That is basically our definition of area in the plane, but it is without an absolute value, so it can be positive and can be negative depending on the relative positions of these 3 points. Now this quantity here that's occurring in the numerator is a very important kind of algebraic construction in mathematics, and it's closely connected with this 2 by 2 array or matrix that's very important in linear algebra. So the matrix x1, y1, x2, y2, whose rows are just the coordinates of our 2 vectors, that has what's called a determinant. Now the determinant is denoted by these square brackets, and the value of that determinant is by definition exactly this quantity. So x1 times y2 minus x2 times y1. The product of those two minus the product of those two. So that determinant is appearing right here as the signed area of this oriented triangle. So yes, in our two-dimensional space, the notion of signed area is both natural and important. Excellent. So now let's go up one dimension to our three-dimensional affine space. And we'll consider the analog of a segment or triangle in this three-dimensional space, which is a tetrahedron formed by 4 points. And we'll put one of those points at the origin, and the other ones will be A1, coordinates x1, y1, z1, A2, and also A3, the corresponding coordinates. So this is a general tetrahedron whose one vertex is at the point O. All right, and we're also going to take these 4 points in a specified order. So O, A1, A2, A3. That order will be represented by this arrow above it, meaning we're talking about an oriented tetrahedron. And corresponding to our notion of signed length of a segment and signed area of a triangle, there's a notion of a signed volume of this tetrahedron. What is that? Well, it's a little bit more complicated. Okay? It involves all of these 9 numbers, as it really must. And it is x1, y2, z3 minus x1, y3, z2 plus x2, y3, z1 minus x3, y2, z1 plus x3, y1, z2 minus x2, y1, z3. All over 6. And in linear algebra, this numerator here is also a determinant. It's a determinant of this 3 by 3 matrix that we form by taking the rows of the 3 points and creating an array or matrix from them. And again, the square bars denote this notion of determinant, which we have not yet defined, but which ends up playing a very important role in mathematics, and we will have to talk about determinants a little while later. All right, so this is the usual notion or definition of what a signed volume is of an oriented tetrahedron, and it really does depend on the orientation. If we interchange 2 of the points, then you can check that the signed volume changes sign. Okay. So you can say, well, we could take the absolute value of this, and then you would get what we usually call the volume. Yes, you could do that, but that would sort of diminish the algebraic naturalness of this definition. Okay, so this is a fundamental definition of a signed volume of an oriented tetrahedron. Now you may well ask, why that factor of 1/6 multiplying the determinant? So that's an analog to the factor of 1/2 that sat in front of the determinant in the triangular case. In the triangular case, we can explain that 1/2 because the determinant by itself is the area of the parallelogram formed by the 2 sides. And the triangle that we're considering is just half of that parallelogram, and so it's reasonable that there be a 1/2 out there. There's a similar kind of explanation for the 1/6 in this three-dimensional situation, but it's a little bit more geometrically involved. And I'm going to leave it to you as an exercise to think about this particular situation here. So here is a cube, say a unit cube, sides are 1, labeled like this. And we're looking at this vertex O here and thinking about these 3 adjacent vertices in the cube, in other words, the nearest neighbors to O on the cube. They form an equilateral triangle. And if you imagine slicing the cube with a plane through those 3 points, then you would separate off a tetrahedron. And the claim is that the volume of this tetrahedron should be 1/6 the volume of the cube. In other words, it should be 1/6. And you can verify that for yourself by a little bit of further slicing of the cube. So see if you can figure out how to slice the cube into 6 tetrahedral pieces which all have the same volume. Once you do that, then you can sort of see, well, if they all have the same volume, then in the volume of any one of them should be naturally 1/6. All right, so our conclusion so far is that signed lengths, areas, and volumes are well defined in one-dimensional affine space, two-dimensional affine space, and three-dimensional affine space, respectively. But let's be careful what that precisely means. It means that the notion of signed length has been defined in the context of A1. The notion of the signed area has been defined in the context of A2. And the notion of signed volume has been defined in the context of A3. But what if we want to mix measurements? For example, what about length, say in A2 or A3? Or area in A3? Just because we have defined the length, or rather the signed length, of an interval on our one-dimensional affine plane does not mean that we have yet defined the notion of length of an oriented segment in our two-dimensional affine plane or in our three-dimensional affine space. Physically, if we use our physical intuition, we don't see any distinction between the segment there, which is on this one-dimensional line, or the segment here, which is in a different position in our three-dimensional space. Because to us, we can move this line from here to here, and clearly nothing about the properties of this line seem to change physically. We must be careful not to transfer that assumption of sort of physical movability of things to our mathematical framework. Okay, it's tempting and maybe a very natural thing to want to do, but we must be careful to avoid introducing this assumption that we can do that. So, for example, very familiar example, going back essentially to the Pythagoreans, 600 years before Christ. In fact, concurrent with the start of serious mathematics in our world. So this basic example, we have an ordinary plane, we have our origin O there, we have this point A, which is 1 over in this direction and 1 over in this direction. Now we know that the quadrance between O and A is well defined. It's this squared plus this squared. 1 squared plus 1 squared, which is 2. But this number 2 cannot be written as d squared for any rational number d. In the one-dimensional case, quadrance is always the square of a signed length. But here, this quadrance between these 2 points is not a square. So it means that although the quadrance exists, the notion of length does not. So we're working here in the rational framework, right? We've agreed that we're going to think about what we can do just with a rational orientation. We can all agree, whether you believe in real numbers or not, that in the rational framework, the quadrance exists while the length does not. So here is a similar kind of example, but going up in one dimension. So here's our x, y, z axes in our three-dimensional space, and here's a point A1, which is 1 along the x-axis, A2, which is 1 along the y-axis, and again, if we look at these 2 points here, the quadrance between them is 2, which is not a square. So again, also in 3 dimensions, we found a situation where the quadrance exists, but the length does not. But we can go a little bit further by looking at these 3 symmetrical points, A1, A2, and A3, forming this little equilateral triangle, each side having quadrants 2. And now if we ask, what is the quadrea of this triangle? All right, quadrea. So our formula for quadrea was involving that Archimedes function, triple quad function. So the 3 quadrances are 2, 2, and 2, so we take 2 plus 2 plus 2 all squared, minus 2 times 2 squared plus 2 squared plus 2 squared. Well, this is 6 squared, which is 36, and we're subtracting 2 times 12, or 24, for a total of 12. Now in the plane, this quadrea, when we defined it, turned out to be 16 times the square of the area. But here in this three-dimensional situation, we see that we're not going to be able to write 12 as 16 times the square of the area. And why not? Well, it's basically because the number 3, which is a factor here, it's a factor of 4 times 3. 4 is a square, 16 is a square, but 3 is not a square. And because of that, we cannot define a rational area of this triangle in this three-dimensional situation. So again, this is analogous to what happens when we go from 1 dimensions to 2 dimensions with length. In 1 dimension, signed length works. But in 2 dimensions, signed length does no longer work. Similarly, in 2 dimensions, signed area of a triangle works. But when we go to 3 dimensions, that notion breaks down in general. So while the quadrea of this triangle exists, the area does not. So this phenomenon is closely related to what I called in an earlier video the price we pay for coordinates. This idea of Cartesian coordinate system to define our mathematical space, which is a very powerful and absolutely crucial development in modern mathematics, going back to Descartes and Fermat. We also have to pay a price for this. It's not entirely free. So in our physical space, length and area seem elementary notions that are independent of orientation. We can move lines around and we can move triangles around in our physical space, and none of their property seems to be affected. In particular, we can measure areas and the areas don't change when we move them. What we're seeing is that in our Cartesian view of geometrical space, in other words, the mathematical view, this is no longer the case. So it turns out that this is true of volume as well. Volume is unambiguous and defined in three-dimensional space. But when we extend it to higher dimensional spaces, it again is generally not defined. Now, note that this insight is largely hidden if you believe in the fairy tale world of real numbers. Okay. This is one of the disadvantages that the dream world of real numbers has. That when you adopt it, you no longer see this very important distinction. Because things are lost if one is sort of willing to believe that there are square roots around that you can just sort of snap your fingers and they are conjured into existence. All right. But with this rational framework, we see that in fact it's a number theoretical issue. Number theory raises its head here. The issue of whether a given quantity is a square or not is exactly the pure mathematical notion that determines whether some length or area exists or not. Right. So we gain something. There's some added complexity in our world, but it's also a richer world that we get by having this rational point of view. And when we move to more general fields, like finite fields and other fields, it's exactly this orientation that we need to structure ourselves correctly. So this introduces what we might call the isotropy conundrum. Okay, which is that all lines in a higher dimensional Cartesian space are not geometrically isomorphic. If we're working in three-dimensional space, mathematically, then this line and this line are not necessarily the same. Isomorphic means the same or equivalent. They are not necessarily the same geometrically. When we make measurements in this line or in this line, we can expect to get different kinds of numbers. Similarly, all planes in a higher dimensional Cartesian space, i.e. in dimensions 3 or higher, are not geometrically isomorphic. It's not automatically true that this plane and this plane have exactly the same geometrical properties in three-dimensional space. I know this is kind of a sort of a given axiomatic idea that almost all mathematicians in the beginning of the 20th century think is self-evident. But it is not only not self-evident, it is also not true. Okay? It just represents a misunderstanding of our geometrical world. We cannot appeal to the physical world and say, oh, it's true in the physical world, and therefore it's true in the mathematical world. That doesn't follow. In fact, we actually don't know whether it's really true in the physical world because we don't understand our physical world as well as we do our mathematical world. Right? Our mathematical world we understand much better. So let me illustrate that with an interesting curiosity. In our two-dimensional Cartesian plane, in A2, there are in fact no equilateral triangles. Because if you had an equilateral triangle like this with quadrants Q, Q, and Q, with these three vertices are all rational points, then if you compute the quadrea of this triangle, it's the sum of the three q's all squared minus 2 times q squared plus q squared plus q squared, you get altogether 3q squared. Because here there's a 9q squared, and here there's a minus 6q squared for a total of 3q squared. But such an expression cannot be 16 times the area squared, because in that case everything here is a square except for 3, which would imply that 3 is a square. So 3 is not a square in rational numbers. So some people who are sort of beginners to this subject get perplexed by this. They say, well, how can it be that there's no equilateral triangles in the rational plane? Well, that's just the way it is. That's the way mathematics is. I'm sorry. But, you know, in the rational two-dimensional plane, there are no equilateral triangles. Okay. Of course, there are approximate equilateral triangles. It's easy enough to get points which are approximately having the same quadrances, but exactly, no, there isn't. But in three-dimensional space, we have just seen that there are, in fact, equilateral triangles. In fact, very simple, elegant ones. For example, the triangle ABC consisting of these 3 points, which are each at the unit position on each of the 3 coordinate vectors. So this triangle definitely exists, that all the quadrances are 2, and we've seen that the quadrea is 12. So in this case, what happens is that the triangle exists, the quadrea exists, but the area does not. Okay. It's the area of this equilateral triangle which is not a well-defined concept. This does not make any sense to say what is the area of that equilateral triangle. You can ask what is the quadrea of that equilateral triangle, and the answer is 12. That's what we can do over the rational numbers in this geometry. All right, so this is all very interesting, and of course there are higher dimensional analogs of this, right? We can sort of see that we're moving up some ladder, 1 dimensions, 2 dimensions, 3 dimensions. The kinds of patterns that we're seeing here in these low dimensions is at least likely to continue on in some fashion if we're able to define things in the right way, if we see some way of extending our definitions. So next time we're going to have another look at this situation and perhaps resolve things to a certain extent, or clarify that in fact sine lengths, areas, and volumes do play a role in these higher dimensions. But it's not an absolute role, it's rather a relative role. So we're going to move to widening our understanding of what measurement actually involves, from this sort of absolute kind of position, which is very popular these days, to a more relative position, which is in fact more in the lines of what the ancient Greeks thought. It's very interesting, the kind of circle of ideas that are coming around here. That in many ways we start to see that the way the ancient Greeks thought about things was actually a more profound way than what we are doing currently. Very interesting. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.